So right now we're talking about how to prove triangles are congruent, and we're going to learn a new theorem today that we call SAS. So let's start with what we just recently did. Last section we learned a theorem called SSS, and that stood for side, side, side. And it said if you have two triangles, and you can show that each of the three sides of one of them is the same as each of the three sides of the other, then those triangles are automatically congruent and you don't even need to know anything about the angles. Well, we're going to learn a few more of these. I call them the letter theorems. We learned SSS and we're learning SAS. Every time we learn one of these letter theorems, we already know that S stands for side, while A stands for angle. So when we say SAS, we're really talking about side, angle, side. And that's the name of this theorem, side, angle, side. And what it says is if side, angle, side of one triangle is the same as side, angle, side of another triangle, then those triangles are congruent. So like yesterday we said if three sides are the same as three sides, the triangles are congruent. Now we have the same thing, but it's two sides and one angle. So what we're saying is, and I'm going to make an important note here, it's two sides and the angle between them. It has to be the angle in between them, and I'll talk about why in just a second. But it's not just any two sides and angle, it's two sides and the angle in between them. And if it's the same in the two triangles, then you don't need to know about the third side. You don't need to know about the other two angles. The triangles are automatically congruent. So here's an example of an SAS triangle. Now the reason it's SAS, and we have some marked sides and angles on this picture, I'm going to color code them to really make them stand out. So right here where there's one mark, and right here where there's one mark, I'll make those the blue sides. Those blue sides are congruent. Now right here where there's two markers, and right here where there's two markers, we'll make those the red sides. Those two sides are congruent. Now notice for the angle, I didn't pick angle F, I didn't pick angle D, I didn't pick A or C. I very specifically picked angle B and angle E because that's the angle that's in between those two sides. So in between the red side and the blue side in both triangles, I marked that green angle. Now because the two sides are the same, the blue ones and the red ones, and the angles in between them are also the same, those two triangles are congruent by SAS. I don't need to know what angle F or angle D is. I don't need to know the top side of the top triangle or the bottom side of the bottom triangle. I can automatically say those two triangles are congruent. This was another picture. Get me out of there. Here's another picture of an SAS triangle, and I'll color code them the same way. So we have one marker here and one marker here. So those two blue sides are the same. We have two markers here and two here, so those red ones are the same. And we have an angle here and an angle here in between the red and the blue. So both of these triangles, both of these are pictures, are examples of two triangles that are congruent by SAS, side, angle, side. All right. So here's what I want you guys to notice about the name of the theorem, SAS. It's very important. Now, this didn't matter for SSS because it was all three sides. There's no order if you're talking about all the sides of a triangle. But for the other letter theorems, it does become important. So the letters of the name of the theorem go in order around the triangle. So what I'm going to do is I'm going to show you an example of two triangles that are not congruent by SAS, even though it looks like they might be. So let's say I drew this triangle right here, and then I drew another triangle over here like this. And let's say I mark, okay, this side is congruent to this side, so that's one S. And let's say this side is congruent to this side, so that's two S's. And then let's say I say this angle right here is congruent to this angle right here. So you look at it and you go, okay, well, there's two sides in one angle that are the same in both triangles. So you might think to yourself, these triangles are congruent by SAS. And that would actually be wrong. These triangles are not necessarily congruent, and it's definitely not in SAS, because if I start, and you can go in either direction, but let's say I'm going this way around the triangle. This is a side, this is a side, and then we get to the angle. This is actually SSA. And that's why I said on the last slide, we need the angle to be between the sides, just like it is in the name. So unless we are talking about this angle right here and this angle right here, the one where I put the red arrow, that's the angle that it would need to be in order to use SAS, because it has to be the angle in between the two pairs of sides that you know are congruent. So the original picture that I drew you there is not congruent by SAS. So make sure you understand, once we get past SSS is kind of the easy one because there's no order to it, it's just all the sides. Once we get past that, all of a sudden order matters. So for SAS, make sure you're being very careful with it. All right, so for our last question today, we're going to go back to that familiar problem where I've been giving you these half proofs where I do the statements and you guys provide the reason. Let's do another one of those. So here's our setup. We have that picture over on the right, and it says given PR is congruent to RT, and R is the midpoint of QS. And we want to prove that triangle PQR is congruent to triangle TSR. So let's start by marking our picture. The one thing I said in the given information is that PR, here, line segment PR, is congruent to RT. So I have one pair of congruent sides. That's also the reason though. See, if you notice, my first statement over here is exactly that. PR is congruent to RT. Now, whenever the statement comes from up here, that's the easiest one. You should never miss this one on a problem, on a quiz or a test or a homework assignment. The reason is given. Okay, now, the second piece of given information says that R is the midpoint of QS. Now, the definition of midpoint is something we talked about in the last assignment. A midpoint, it means middle point. I mean, it kind of tells you what it is. A midpoint is the line exactly halfway on a line, or the point exactly halfway on a line segment, and it cuts it into two equal or congruent pieces. So Q is here, S is here, R is the midpoint. That means that QR here is congruent to RS here. And that's our next statement. QR is congruent to RS. So you think, all right, how did I know that? It's not given. I didn't tell you in the question that QR is congruent to RS. What we did is we used this to figure it out. So my reason here is the definition of midpoint. It's because we know what the midpoint means. It means it cuts that line segment in half and creates two congruent pieces. So we're now done with the given information. Let's keep going on the proof. Let's look at what's next. So what's next is an angle. And it says angle PRQ. So if you start at P, here, then go to R, here, then go to Q, here, you're talking about this angle right there on the top. From P to R to Q. Remember, when you're doing angles, the letters go in order and they draw the angle itself. Now that one is congruent to angle TRS. So that goes from T to R to S. That's this angle here. So I mark it on my picture, and then I ask myself, what's the reason? How do I know that? Well, those are vertical angles. That's one thing we've done a lot of this year. Remember, when two lines cross and make an X, the two angles opposite each other are called vertical angles, and they're always congruent. So we can say vertical angles. It's actually the vertical angle theorem. But if you don't say theorem, that's okay. If you just put vertical angles, I'll know what you meant. So now we get to the actual end of the proof. Whatever you see here should be what you're trying to prove. Now you always have to give a reason for it. Let me talk about a real common mistake. Everybody thinks because the first reason of a proof is given, then the last one is prove, and they just write the word prove. I'll tell you this is a 100% rule. The reason in a proof is never the word prove. If you write prove in a proof, that part is wrong. 100% of the time, you will never, ever, ever have a reason that is the word prove. We have to have an actual reason. Now the reason is the theorem we just learned. It's an SAS, because look what we have. If you look at the top triangle, it goes red marker, green angle, blue marker, and the bottom triangle, red marker, green angle, blue marker. That's side, angle, side. So your reason is SAS and you're done with the proof. So that's providing reasons in a proof. You're going to see some of those in the assignment today. Remember the things we talked about. Usually the first 1 or 2 reasons is given. Just look at what's given and see if it matches. The middle steps, make sure you're looking and just asking yourself why that statement is true. And it's usually things like definitions and theorems and postulates that we've learned. And just remember for the last step, it's never prove. The reason will never be the word prove. It's going to be just like the middle steps. It's going to be some sort of theorem or something like that.